In this video, we're going to look at explaining what is meant by the term conservation of mass and applying it to chemical equations. We'll also explain why the mass can appear to change when a product or reactant is a gas. And finally, we're going to calculate the MR, or the relative molecular mass, of a molecule or compound. The conservation of mass is a principle in chemistry which states that during a chemical reaction, no atoms are made or destroyed. This means that in a chemical reaction, the total number of atoms will stay the same. So there'll be the same number of atoms on the reactant side as the product side. We just rearrange them. We don't add any atoms and we don't destroy any atoms. So for example, in this case, we've got a chemical reaction showing that the reactants are 2 magnesium atoms reacting with 1 molecule of oxygen, O2. And this produces 2 molecules of magnesium oxide. So you can see here we've got the same number of atoms on each side. We've got 2 magnesium atoms in the reactants, and we've got 2 magnesium atoms in the products. We've got 2 oxygen atoms in total in the reactants, and we've got 2 oxygen atoms in total as the products. So the number of atoms in total has stayed the same. We can also apply this to the masses of the reactants and the products. So if we react together 10 grams of sodium hydroxide with 20 grams of hydrochloric acid, well, there's 10 grams and 20 grams for each of the reactants. That makes 30 in total, which means the total mass of our products must also be 30. So we haven't made or destroyed any atoms, so we can also say the total mass of the reactants, 30 grams, must equal the total mass of the products, so that must also be 30 grams. In the next video, when we look at moles calculations, for those of you studying higher tier, you'll be able to work out the mass of each of the products, but they'll both add up to 30 grams. For the moment though, we just need to be happy that the total mass of the reactants will equal the total mass of the products. So if we've got 30 grams of reactants, we're going to have 30 grams of products. There are 2 cases though, where if you were to carry out this process experimentally and you were to record the mass before and afterwards, it could appear to increase or decrease. Now we know from what we've just learnt about that that can't actually be the case because the total mass must stay the same, but we're going to look now at how the mass could appear to increase. So as we've just looked at, if we react together 10 grams of magnesium with 20 grams of oxygen, we know we should produce 30 grams of magnesium oxide. But let's look what happens if we were to do this process experimentally. At the start of the reaction, we would see on the balance 10 grams, and at the end we would see 30 grams, so it makes it appear as if the mass has increased. But we need to look at why this is the case. In this reaction, we're reacting the oxygen with the magnesium, but the oxygen is a gas, and you can't record the mass of a gas on a balance because it's not putting any force down on the balance. So because of this, even though there is oxygen in the flask reacting with the magnesium, the balance will only show 10 because it can only record the mass of the solid, in this case the magnesium. So we can therefore say as a general rule that whenever a reactant is a gas, the mass will appear to increase. Because we start off with just the mass of the solid, just the mass of the magnesium, we react with the oxygen, which is present in the air, and that will form our magnesium oxide, which we know because we're reacting 10 grams of magnesium with 20 grams of oxygen must have a total mass of 30 grams. But it appears if it's increased, but we know the total mass of the reactants was also 30, we just couldn't record the mass of the oxygen on a balance because it was a gas. The same can be true for when the mass appears to decrease, so let's look at why this might happen. So for this reaction, we can see if we react 10 grams of magnesium with 20 grams of hydrochloric acid, we should produce in total 30 grams of magnesium chloride plus hydrogen. But let's look what happens if we did this experimentally and what values we would see on the balance. So we'd see the mass would start off at 30 grams for the 10 grams of solid magnesium and the 20 grams of the aqueous hydrochloric acid, but it would show us a final reading of 25 grams, making it seem as if the mass has decreased. Now we know from our conservation of mass principle that that's impossible. The total mass before has to equal the total mass afterwards, so let's look at why it might look like the mass has gone down. And this is because the mass of hydrogen can't be recorded on the balance because it's a gas. So again, just like when we looked at the example of why the mass could increase, we can't record the mass of a gas on the balance. We can only record the solid or liquid or aqueous constituents. So we start off with 30 grams. The gas produced can either escape from the container, or even if it's still in this part here, we still can't record the mass of it. So because of that, it will appear as if the mass is decreasing, but that just means we've essentially produced 5 grams of the gas and it can't be recorded. So as a general rule, we can say that whenever a product is a gas, the mass will appear to decrease, but you know we've still produced that gas and its mass is still there, we just can't record that mass. We're now going to look at the periodic table and calculating the MR, which stands for the relative molecular mass, which we'll look at in a second. It'll be really helpful if you've got your periodic table out at this point, but there's one here which you can pause the video on and screenshot in case you don't have yours with you. So I've zoomed in on a small section of the periodic table, and we're just going to look at this key for a moment. So we're going to look at what the atomic symbol is, what the relative atomic mass is, and what the proton number is. We're going to use sodium as an example for each of those. So the chemical symbol for sodium is Na. The atomic number tells us the number of protons the element has. So for this AQA periodic table, it is written below the atomic symbol. However, on some periodic tables it might be written above. These numbers can be either way around, which is why it's important to check the key so you know which number you're looking at. The atomic number will always be the smaller out of the atomic and the mass number though. So the smallest, or in this case the number on the bottom, is the atomic number. For sodium, this is 11, which means sodium has 11 protons. It also means that it'll have 11 electrons, because we know the number of electrons is always the same as the number of protons. For the AQA periodic table, the number above the atomic symbol is the relative atomic mass, or the mass number, and this is the number of protons and neutrons added together. So for sodium, this number is 23, which means in total, sodium has 23 protons added to neutrons. Now we know sodium has got 11 protons, so if it has 11 protons, that must mean it has 12 neutrons to take the total of both of those up to 23. Now we looked at this in more detail in the first topic when we looked at the periodic table, so if you're unsure on any of these three things, go back and have another look over that topic. We're going to be focusing on the mass number for the rest of this video to work out the relative molecular mass. So MR stands for the relative atomic or molecular mass. I'm going to look at an example of what this means. So for the element magnesium, it just has a relative atomic mass of 24, so we could almost say its relative atomic mass is just 24. There's no calculation to do here, and we can just find the values straight from the periodic table. So for any atom by itself, its MR, or sometimes called its AR for its atomic mass, is just the relative atomic mass given straight from the periodic table. So for example, carbon would have a relative atomic mass of 12, because that's its value from the periodic table. If we were looking at magnesium oxide and we wanted to find its relative molecular mass, we would need to add together the relative atomic mass of magnesium and the relative atomic mass of oxygen. So magnesium has a relative atomic mass of 24, and oxygen has a relative atomic mass of 16. So to work out the relative atomic mass of magnesium oxide, we would do 24 plus 16, which would give us a final answer of 40. We would do exactly the same process for working out the relative molecular mass of hydrochloric acid, HCl. We would do 1 plus 35.5, because hydrogen has a relative atomic mass of 1, and chlorine has a relative atomic mass of 35.5, so we would add these two values together and get a final answer of 36.5. For carbon dioxide, we need to take into account what this little number 2 means. So if there's a little number or a subscript number after an element, it means there's that number of that particular atom in the molecule. So CO2 means there's one carbon, because if there's no little number after an element, we assume that little number to be 1. So there is one carbon atom, and there are 2 oxygen atoms. So CO2 is made of 1 carbon and 2 oxygens. So to work out the molecular mass of CO2, we're going to do 12, which is the relative atomic mass of carbon, added to 2 lots of 16, because there are 2 oxygens, and each oxygen has a relative atomic mass of 16. So doing 12 plus 2 lots of 16 will give us a total of 44. If we're looking at Na2O, this means in this compound we're going to have 2 sodium atoms, because there's a little number 2 after the Na, and 1 oxygen atom, because there's no little number after the oxygen, so we must just have 1 oxygen. So to work out the relative molecular mass, we would do 2 times 23, because there are 2 sodiums, and sodium has a relative atomic mass of 23, added to 16, because there's 1 oxygen, and oxygen has an atomic mass of 16. Giving us a final answer of 62. If we're looking at magnesium hydroxide, we've got some brackets and then a little number. So let's look at what this compound looks like. So in magnesium hydroxide, we've got 1 magnesium atom, and then we've got 2 lots of everything inside the brackets. So we've got 2 lots of OH. So we've got an OH, an oxygen and a hydrogen up here, then another oxygen, hydrogen down here. So let's look at how we could put this into the equation. So we would do 24, because we've got 1 magnesium, and magnesium's got a relative atomic mass of 24, plus 2, because we've got a brackets and a little 2 here, which means we need 2 lots of everything inside the brackets. So 2 lots of 16 plus 1, because oxygen has got a relative atomic mass of 16, hydrogen's got a relative atomic mass of 1, so we need to add those together, do 2 lots of them because they're in the brackets of little number 2, and then add that to the 24, which will give us a final answer of 58.